Lewis dot structures are a symbolic device used to represent bonding and electron structure in atoms and in molecules. So basically, you draw the chemical symbol, which in this case is nitrogen, and then you draw dots around the symbol, and those dots represent valence electrons. So they are the electrons of the highest n level for main group elements, and we don't usually use dot structures for anything other than main group elements. So some examples. In group 1A, all of the elements have a single valence electron. So lithium would have one dot. Sodium as well would have one dot. In group 2A, you have beryllium, and that has two valence electrons. It's group 2A, and we generally put them on opposite sides of the symbol. Magnesium is another example, has a dot, two dots for the two valence electrons. And when you're talking about metals, like group 1 and 2A, for instance, those dots, which are the valence electrons, represent the electrons that the metal atom will lose when it becomes a cation and does ionic bonding. Okay, so the dots show the number of electrons that are lost to form ionic bonds. Okay, and then if we go over to group 4A, you have four valence electrons, and we put one on each side. Okay, so carbon's an example, silicon is another example. And then let's jump one or two groups and go to group 6A, like oxygen, and you start by putting one on each side, and then it's kind of like when we do electron configurations, you double them up when you need to. Okay, so same thing with sulfur. 1, 2, 3, 4, 5, 6. And which side you double them up on is not crucial for just a single element. Alright, and group 8A, such as the noble gases like neon, have 8. So we put 2 on each side of the atom. So neon looks like that, argon looks the same. Okay, and the reason that we only use them for main group elements, you might guess, is because they follow the octet rule, which I'm going to tell you now. Okay, the octet rule tells you that bonding involves the gaining of electrons, losing, or sharing of electrons to attain a noble gas configuration. In other words, 8 electrons, so that's why octet. And I needed to say up here, the nonmetals will show valence electrons that you add to become like a noble gas, or they're the ones that can be shared. So either they show the electrons to share, oops, or they show the ones to gain, or they show what to gain. They show the number to gain. Alright, let's talk about, so that's how to do Lewis dot structures for individual atoms. Now we're going to talk about how to draw Lewis structures for molecules. Okay, and there's going to be 4 basic rules and then a few additional rules later. So, first thing you need to do is place the atoms for your molecule, and there's some general guidelines for placing them. Put the lowest electronegativity in the center. Okay, so if we look at a compound such as CH3Cl, the carbon goes in the center because it's lowest, and frequently the first element goes in the center. So carbon goes in the center, and we can put the other elements around it. Okay, so carbon generally goes in the center, and hydrogen is always going to be on the outside, and that's because it cannot form more than one bond. And let's do another example while we're at it. SeCl2, so the least electronegative atom would be selenium, whoops, chlorine. So we place our atoms like this. All right, step 2. Add up the total number of valence electrons. We'll do the same 2 examples. CH3Cl and SeCl2. Selenium dichloride. All right, carbon. We have 1 carbon, and that has 4 valence electrons. We have 3 hydrogens, each of which have 1. So it's 1 times 3 equals 3. And chlorine has 7. So we have a total of 14 valence electrons. Selenium is in group 6, so it has 6. Chlorine has 7, and we have 2 of them. And when we total those all up, we have 20 valence electrons for selenium dichloride. All right, let's go to step 3. We're going to use 2 electrons for each bond. So let's remember how we had these set. Here's how the atoms were placed above. Okay, so we're going to use 2 electrons for each bond. Now you remember this one had 14 electrons and this one had 20 electrons. All right, so we'll use 2 there, 2 there, 2 there, and 2 there. And so that is 2, 4, 6, 8 electrons used, which means we have 6 left. Over here, we'll use 2 there and 2 there, and so we have used 4, which means we still have 16 left. Next rule. We distribute the remaining electrons to make octets, except hydrogen, because hydrogen does not take an octet. All right, so far we had this. And we said we have 6 left. So we'll put, hydrogen doesn't take an octet, and carbon already has one. Right, it's got 4 single bonds, each of which is 2 electrons. So we'll put the 6 over here, and now chlorine has an octet because it has all of this. Carbon has an octet because it has all of this, and notice these represent shared electrons. So chlorine has 8 around it, carbon has 8 around it, hydrogen never gets 8 around it, it only gets 2. All right, so let's go to selenium dichloride, and we had 2 there, and we still have, how many do we have left? 16. Okay, so let's start putting electrons out to make octets. So that's 2, 4, 6, 8, 10, 12, 14, and 16. So now we have an octet around each one. Chlorine has this octet, 8 electrons. Each bond is 2 electrons. Selenium has these electrons to make its octet, and chlorine has these electrons to make its octet. Notice the shared ones are the bonds. All right, so those are the 4 basic steps for drawing molecular Lewis structures. And so you should try drawing one using those same 4 steps for OF2. Now, these are both very electronegative atoms, but the least electronegative is oxygen, because fluorine is the most electronegative atom there is. So that's how we place the atoms. Then we count valence electrons. Oxygen has 6, fluorine has 7, and there's 2 of them. So we have a total of 20 electrons. All right, so first we'll use 2 to make each bond. So we've used 4, and we have 16 left. And now we will place the rest around to make octets. Fluorine now has 1. Oxygen now has 1. And the other fluorine now has 1. And again, I'll show you the octets. one for fluorine, one for oxygen, one for the other fluorine, all octets. Okay, we did 4 rules. Now I'm going to add a 5th rule that might come up sometimes, and that is if you get to rule 4 and there aren't enough electrons to make octets, then you have to draw multiple bonds. All right, let's do some examples of that. C2H4 and Cn-. All right, if you start, we're just going to count up valence electrons. Carbon has 4, the other carbon has 4, and the 4 hydrogens have 4, so that's 12 valence electrons. Now, cyanide, Cn-, carbon has 4, nitrogen has 5, because it's in group 5, but you have to add 1 because it's negatively charged. There's an additional electron there, so we add 1 more, and we get 10 electrons. So if there's a charged species, you need to add or subtract electrons accordingly. All right, so let's place atoms. C2H4, we're going to place the carbons in the center, and we're going to put hydrogens around them, and we're going to make it symmetric. There's no reason not to. And Cn, there's not a lot to place. There's no central. They just go next to each other. Okay, so now we're going to first draw single bonds. Whoops, that doesn't work. I'm going to have to redraw this, I think. I'll redraw the hydrogens and we'll make single bonds. I'll make a single bond there. Okay, so we've just used 10 of the electrons and we have 2 more, so we're going to put them on the carbons. But notice that there aren't enough electrons to make an octet around the carbons. They are each 1 short of an octet. They have 6 that are bonded, and then they have an additional 1 that makes 7. All right, let's do cyanide. There are 10 electrons. We do 1 bond between. We start placing the other electrons. We have 8 left. We just did 6. And there's 8. And there aren't enough for octets on both of them. You could start at the nitrogen, but there wouldn't be enough for the carbon. And one thing to note, when you're doing negatively or positively charged Lewis structures, you have to use a bracket and put a minus sign. This is separate, of course. Put the charge outside of it. All right, so neither one of these 2 examples has octets. The octet rule satisfied. So we are going to continue and make multiple bonds. So next step here is we need to share more electrons. Okay, that's what making multiple bonds is. So take those 2 dots and make them shared between them. They each want 1 more. They could each share. And we do that by drawing a double bond. And now this carbon has 8 electrons, and this carbon has 8 electrons. They've shared 4 now, okay? 4 electrons are shared. And we say that the bond order between the carbons is 2. A single bond is bond order 1, double bond is bond order 2. Pretty simple. All right, so we're done on the left. Now we're going to go on the right, do cyanide. We're going to share additional electrons. Okay, we're going to take these 2 that are below and put them into the bond. So we make a double bond, and now nitrogen has these 2, and there's 4 on the carbon. I'm going to distribute them a little differently just so it looks symmetric. And we have to do the bracket, and we have to do the negative sign because it's charged. All right, are there octets? No, still no octet. Okay, we had no octet here. We still have no octet here. So we need to share more. We're now going to take these electrons and put them in the center and make a triple bond. And then we'll put the dots on the outside just for symmetry. And now carbon has an octet, nitrogen has an octet. Don't forget, we need brackets and a negative sign. trying to move down here. Okay, and we say that it has a bond order of 3. And that happens for 6 shared electrons. All right, and don't forget, I just want to remind you, use brackets. And charge when you have an ion. All right, and there's one more case I would like to mention that will occur once in a while when there aren't enough electrons. There are some systems that don't need a full octet, that are stable without a full octet, and those are generally when you have boron or beryllium in the atom, they will be happy with less than an octet. They do not follow the octet rule. So these are an octet exception. And that will come up some. All right, so it's time for you to try drawing things. Draw loose structures for ammonium, ion, remember the rules for ions, and carbon monoxide. And then answer the question, how many electrons are in single bonds, how many double bonds, how many triple, how many are not bonded at all. Okay, so let's stop the tape and work on that. All right, let's draw the structures. For ammonium, your total number of valence electrons, you should have 5 for nitrogen and 4 for hydrogen. And then you subtract 1, minus 1. So it's actually 8 electrons. And carbon monoxide, you should get 4 plus 6, so you should get 10 electrons. All right, so we can draw them. We would place the least electronegative thing in the middle, except we can't with hydrogen because they cannot be in the center. Hydrogen has to be on the outside because they can't have more than one bond. All right, so we'll draw, I'll have to start that over, maybe. Nope, I can do it. So we use all 8 electrons just by drawing the single bonds. We then don't forget to put brackets, and we're done with that one. We'll answer the questions in a minute. Carbon monoxide, you should end up with a triply bonded structure in order to get octets around everything, and 10 electrons. All right, so how many single bonds? There's 4 here. No double bonds, no triple bonds, and none not bonded electrons. For carbon monoxide, you have a triple bond. No single, no double, and you have 2 sets, or 4 total electrons that are not bonded. All right, one more addition to our rules. We had 4 rules, and then the 5th one was if there aren't enough electrons to make octets. Now we're going to do the case of what to do if there are too many electrons to make octets. So it turns out that atoms in period 3 or row 3 or more can take more than an octet. We said that boron and beryllium can take less than an octet, and we can make multiple bonds to make octets, but we also find some atoms, particularly phosphorus and sulfur and chlorine, will frequently take more than an octet. There are others. There's xenon, there's krypton, there's others. Okay, so one example is sulfur hexafluoride. Okay, sulfur hexafluoride has 6 fluorines on it. Okay, so I'm going to draw using the notation where you use wedges, and the fat part of the wedge is coming out of the paper at you, and the skinny part is going back into the page. So this is sulfur hexafluoride. It has 6 bonds, 6 single bonds to fluorines, and each of these fluorines also has an octet around it, but it's not letting me draw them. And I think you can imagine that for yourself. There we go. I'll do it on one of them. So each fluorine has 6 additional unbonded electrons, and there are 6 total bonds, each of which has 2 electrons, so there are 12. Okay, sulfur has 12 electrons around it. The Fs will all have an octet. Okay, the fluorines cannot have more than an octet because they are not period 3 or greater. They are period 2. So they can't have more than an octet, but the sulfur can. All right, and one more thing for you to try. Draw Lewis structures for these last 2 species. Stop the tape and practice. HCN, we're going to put carbon in the center. And count up your valence electrons. I think you'll find that carbon has 4, nitrogen has 5, hydrogen has 1, so that's 10. So we're going to end up with 1 there and 1 there, and I'm not going to go through it all, but you're going to need to have a triple bond for between the carbon and nitrogen. So you can't have more than a single bond to the hydrogen. That's not allowed. And you're also going to have 2 extra electrons on the nitrogen. I'm going to redraw that a little nicer. So there's HCN. All right, phosphate anion. You should remember that the phosphate anion is PO4 3-. Okay, so how many electrons do we have? Phosphorus has 5. We have 6 for oxygen, but there's 4 of them, so we get 24 there. And then we have to add 3 more because it's 3-. So that's 8 more, so that's 32 valence electrons. All right, so start drawing. The phosphorus has to go in the center because it's the least electronegative, and you can draw single bonds, and you can draw lots of electrons around the oxygens. Make octets around all of them. You have an octet around the phosphorus. This is not actually, this is a valid Lewis structure for what we've shown you already, although it turns out there is actually, phosphorus actually does have more than an octet in the phosphate anion, but this is a perfectly valid Lewis structure given what we've talked about so far. We will soon talk about things that would tell you this is not the most ideal Lewis structure. But you can get octets around everything. Don't forget the brackets and the 3-.